Welcome to this explainer. Today, we are going to transform the messy physical reality of electrical circuits into beautiful, predictable mathematical order. If you've ever stared at a complex schematic, with wires, resistors, and sources weaving together like some kind of technological spaghetti, and felt a wave of absolute panic, you are in exactly the right place. We're going to take all that visual chaos and translate it into clean, elegant linear algebra. Here is exactly what we're covering today. 1. The analytical paradigm shift. 2. Identifying sources and paths. 3. Rules of shared boundaries. 4. Constructing the circuit matrix. And 5. The beauty of symmetry. Let's dive in. Starting off with Section 1, the analytical paradigm shift. So why do circuit equations almost always end in algebraic errors? If you're an engineering student, or honestly just a dedicated hobbyist, I guarantee you've asked yourself this at 2 a.m. You spend an hour tracking every single current, you fill up 3 pages of a notebook with math, and somehow you end up with -4 amps when it should definitely be +2. It is incredibly frustrating, right? Well, the culprit for all that hair pulling is almost always the old branch method. It creates this chaotic web because you're literally tracking every single wire and every junction split. You end up needing a massive system of equations, one for every single branch, which is practically begging for human error. But the mesh method, it is a total game changer. By zooming out to track continuous closed circular paths, we get to completely ignore those junction splits. This drastically cuts down your independent equations and is perfectly optimized for complex, multi-source systems. So how do we actually pull this shift off? Here's your procedural playbook. It's 4 concrete steps to translate any chaotic circuit into an organized matrix. Phase 1, identify your sources. Phase 2, assign continuous paths. Phase 3, extract local rules using KVL. And finally, Phase 4, construct the matrix form. Stick to these 4 steps and your analysis is going to be bulletproof. Moving right along to Section 2, identifying sources and paths. Okay, before we even touch a schematic, we absolutely have to lock down the positive sign convention. It sounds super basic, but a positive sign strictly means that terminal A's potential is higher than terminal B's. That's it. But this seemingly simple rule is the entire baseline for Kirchhoff's laws. If you don't anchor this concept first, trust me, your matrix is going to fall apart before you write your very first equation. Kicking off Phase 1, whether your voltage and current sources are DC or time varying, applying that positive sign convention gives us our baseline. Your very first job with a new circuit is just to scan the board, find those independent sources, and boldly note their polarity. They act as the independent drivers of our entire system. Now into Phase 2, and this is where we introduce a massive analytical abstraction. We are completely leaving behind the physical reality of currents crashing into junctions and splitting apart. Instead, we're modeling continuous analytical loops. And here's the golden rule. Assume all our continuous mesh currents flow strictly clockwise. Now sure, real electrons do not care about our clockwise rules, but by enforcing the standard analytically, we're basically setting a trap to capture mathematical symmetry later on. It's a brilliant hack. Let's look at Section 3, Rules of Shared Boundaries. Because these loops don't exist in a vacuum, they inevitably share components. So when they collide at a shared resistor, who wins? You have to use the rule of the dominant loop. Think of it like home turf advantage. The loop you are currently analyzing is always dominant, meaning it automatically claims the positive variable. The neighboring loop's current gets strictly subtracted. For example, from loop 1's perspective, the current is I1 minus I2. But hop over to loop 2's perspective and it instantly flips to I2 minus I1. Master this one boundary rule and you eliminate 90% of your algebraic mistakes. Part 4, constructing the circuit matrix. With our boundary rules set, we hit Phase 3, extracting local rules using Kirchhoff's voltage law. By tracing our raw clockwise path, we write out the long-form equation. Then we do a really crucial mathematical cleanup. We algebraically group our unknown variables, our currents, on the left side of the equal sign, and we shove all our known independent sources over to the right. We are intentionally sorting the unknown from the known. Let's scale this up to a 3-loop system. And hey, don't let the visual complexity freak you out because the rules literally haven't changed. We systematically apply that exact same grouping process to Mesh 1, Mesh 2, and Mesh 3. By doing this, we generate a robust set of equations that maps the self-resistance, the total resistance inside one specific loop, against the shared resistance overlapping with its neighbors. And here's the absolute magic trick of Phase 4. We take all those sprawling, intimidating equations, strip away the clutter, and drop the coefficients neatly into an empty matrix structure. The entire complex system completely reduces to the foundational format of R times I equals V. Your resistance matrix multiplied by your current vector equals your voltage vector. Suddenly, all that chaos is perfectly contained.
Finally, Section 5, the beauty of symmetry.
This is the payoff, this symmetry reveal, where chaotic physical realities become perfectly balanced matrices. If you diligently followed that all-clockwise rule from Phase 2, and you strictly adhered to the dominant loop subtraction rule in Phase 3, you are guaranteed this next result. Just behold the symmetry here. In your resulting matrix, your main diagonal, running top left to bottom right, is absolutely always a positive sum of the physical resistors present inside that specific mesh. And those off diagonals, the ones representing the shared resistors, they're always perfectly mirrored negatives. This acts as a built-in error check. If your matrix doesn't perfectly mirror itself across that positive diagonal, you instantly know you dropped a minus sign somewhere. It self-diagnoses its own errors. How cool is that? This perfectly unifies our entire journey from chaos to order. You've got the circuit environment with its self and shared resistances feeding into the R matrix. You have the continuous path method feeding into the unknown I matrix. And you have the independent source inputs feeding into the V matrix. We have officially transformed physical circuit topology into elegant, predictable, and highly computable linear algebra. You now have the foolproof playbook to eliminate those annoying algebraic errors forever. By shifting your paradigm from splitting branches to continuous meshes and relying on mathematical symmetry, you are completely in control. So now that you can instantly transform any chaotic circuit into a perfectly symmetrical matrix, what complex system are you going to decode next? Grab a schematic, set your loops clockwise, and let's build some beautiful matrices.